Okay, picture this. You're staring down a massive, towering stack of 5,000 exams sitting on your desk. I mean, just grading them by hand would take weeks of tedious, totally mind-numbing effort. But what if you could process every single one of them, calculate all the percentages, and assign precise letter grades in literally less than it takes to blink? Seriously, how do you actually grade 5,000 exams in a fraction of a second? Well, the answer lies in the fundamental logic of computer programming. Welcome to this explainer. Today, we're going to learn exactly how to solve massive, repetitive tasks, like our monumental grading challenge, using foundational code logic in the C programming language. We're zeroing in on C control structures, which are basically the absolute backbone of automating the tedious parts of our lives. To really get how this works, we need to nail down what these structures actually are. Control structures are programming constructs that dictate the flow of code execution, allowing for decision-making and repetition. Think of your code like a car driving down a highway. Without control structures, that car can only drive in one straight line, completely oblivious to stop signs or sharp turns. Control structures, they act as the intersections, the roundabouts, and the detours that tell your car exactly where to go, when to stop, and when to turn around. So here's our roadmap for this problem-solving journey. We'll start with directing execution flow, move into making simple choices with if-else statements, tackle multi-way grading for complex rubrics, scale the whole thing up with loops, and finally, master loop control with break and continue statements. Let's get into it. First up, directing execution flow, because every successful automation journey begins with managing the basic direction your code travels. Okay, let's dive into this. To build an automated grading system, we essentially have four main tools at our disposal in C. First, we have branching statements, things like if and if-else, which act as intersections where the code literally has to make a choice. Second, looping structures, like while or for loops. These act as roundabouts, letting us cycle through the exact same action multiple times. Third, nested control structures, which let us put intersections inside of roundabouts to build highly complex routes. And finally, jump statements, like break and continue. These are your emergency exits. Oh, and a quick pro tip. While C technically has a jump statement called goto, modern programmers avoid it like the plague because it creates messy, completely unpredictable spaghetti code. So we're definitely sticking to the clean, structured routes. Moving right along to Section 2, simple choices, specifically if-else statements. Now that we have our map, we need to establish the basic branching logic to figure out a single student's baseline success. This brings us straight to Task 3 from our source material. We need to implement a C program to determine whether a student has passed or failed based on minimum passing criteria. Basically, we're giving our automated teacher a very simple, binary question to answer. Did the student pass? Yes or no? And this right here brilliantly illustrates the power of the if-else statement. We're using relational, logical, and conditional operators to power this simple two-way branching decision. So if the student's score is greater than or equal to the passing mark, let's say it's 40 points, the program executes the F block and boom, marks them as a pass. But if that criteria is not met, the program automatically reroutes down the else block, marking them as a fail. It is an instant fork in the road based purely on the data we feed into it. Section 3, multi-way grading. We're raising the stakes now because, let's be real, in the actual world of education, a simple pass or fail usually just doesn't cut it. Our next challenge, identified in the source text as Task 4, requires us to calculate a student's total percentage from marks obtained across 5 different subjects and then categorize that result into a specific grade category. This means we're leveling up. We're combining arithmetic operations to find the percentage with complex multi-way decisions to assign the right label. So let's break down the exact grading rubric we need to implement. Getting 75% or higher earns a distinction, 60% or higher is first class, 40% or higher is second class, and anything below that is a fail. To categorize these specific results in C, we can bring in multi-way decisions like the switch statement. It acts like a super smart sorting hat, dropping the student's score into the exact right category every single time. All right, Section 4, scaling up with loops. Because writing code to run just once for one exam is totally fine, but running it manually over and over for a whole classroom, that is a nightmare. Our goal for Task 5 in the curriculum is to generate and print the results of 5 different students. Now, sure, 5 is a small number, but it introduces the absolute necessity of iterative structures. Whether it's 5 students or 5,000, we absolutely do not want to copy and paste our grading logic over and over again. We need loops. Let's pop the hood and break down the anatomy of a loop. step by step. C gives us three main iterative structures: the while loop, the do-while loop, and the for loop. But you know what? They all share a very similar beating heart. First, we initialize a counter, say student number 1. Second, we check the loop condition. Is our student number less than or equal to 5? If yes, we proceed to step 3 and execute all that brilliant arithmetic and multi-way grading logic we just built. Finally, in step 4, we update the counter to student 2, and the roundabout spins again. This simple 4-step process prevents us from writing the exact same block of C code 5 times over. It saves time, and it saves massive amounts of memory. And here is the payoff. When we combine our arithmetic, our multi-way decisions, and our iterative loops, we can process entire datasets instantly. Just look at this hypothetical output for our 5 students. The loop pulled in the data, the arithmetic calculated the percentages, the branching logic categorized them, and we get this beautiful final tally. 2 distinctions, 2 first-class grades, and 1 fail. Our automated teacher works absolutely flawlessly. Finally, Section 5, break versus continue control. To wrap up this explainer, we're going to look at a true master-level topic. How exactly do you manage the flow from the inside of those loop roundabouts? Let's visually contrast these 2 jump statements, because they're real game changers. Imagine you're grading those 5 exams, but you suddenly realize the 3rd exam is entirely blank. Well, you obviously don't want to run the complex grading math on a blank test, right? If you use a continue statement, the program simply skips the rest of the math for student number 3 and immediately jumps to the next iteration, starting fresh on student number 4. It just skips a step. But what if you encounter a critical error, like a corrupted file, and you need to stop the whole grading process immediately? That is where you use break. The break statement is pulling the fire alarm. It is an emergency exit that escapes the iterative loop entirely, terminating the repetition right then and there. By mastering control structures, from the simple intersections of an if-else statement to the multi-way decisions of a grading rubric, right down to the powerful roundabouts of loops, you gain the ability to process immense amounts of data in just a fraction of a second. The logic of C programming isn't just about computers, guys. It's a brilliant framework for highly efficient problem-solving in general. So I'll leave you with this to think about. Now that you understand the mechanics of branching and looping, what tedious, repetitive task in your own life could you automate with a simple loop? Think about it. Thanks for joining me, and we'll see you in the next explainer.